The video for section 5.2 is broken up into two parts. In the first part, we cover the theory of how to integrate over a generalized region in the XY plane. In part two of this, we look at the last two applications of double integrals over generalized regions, computing the area between two curves in the plane, and finding the average value. Then we turn our attention to improper integrals. Let's now turn our attention to the next application of double integrals. This is finding the area of a plane-bounded region. In other words, the area between two curves in the XY plane. To do this, we'll do the same thing we did over rectangular regions. We'll allow the integrand to be a +1. So the area of a plane-bounded region D is defined as the double integral over the region of 1 dA, where the integrand is 1. Let's now look at example 8. Find the area of the region bounded by the curves given by the x-axis, the graph x squared minus 4x, and the graph g equals 2x minus 8. We want to write this as a double integral first, and then as a double iterated integral. In order to determine what we need to do, we need to analyze the shape. Should it be a type 1? Should it be a type 2? To help us do that, notice that if I go with a type 1, I'm looking at above and below and drawing vertical lines of different regions. In this case, I would need 3 vertical lines. I would need one at x equals 0, another one here at x equal 2, and another one at x equal 4. This would divide my region into 2 different regions. I would have one on the left and one on the right. When I'm looking at that, notice that I have the same curve on the top, which would be my y equals 0, the x-axis. But what's on the bottom varies depending on which side I'm on. Between 0 and 2 for x, I have the horizontal line y equals 0 on top and the parabola x squared minus 4x on the bottom. When I'm in region 2, I have again the line y equals 0 on top, but I have the line y equal 2x minus 8 on the bottom. Working this as a type 1 requires us to do 2 double integrals and 2 iterated integrals, 2 sets. What about working this as a type 2? If we do a type 2, do we have different y values? Do we have different curves on the left and on the right? When we're looking at this particular one, let's envision this as a type 2 by drawing horizontal lines that bound the region and where we change which curve is on the left and which is on the right. In this particular case, I always have the left arm of the parabola on the left side and the line on the right side. I think that this problem would probably be easier to do as a type 2, depending on what the functions look like when you get them solved for it and how difficult it would be to integrate with them. You can make your choice now as to whether you want to work it as a type 1 or a type 2, follow through, and then turn the video back on and we'll take a look at both of these together. So let's take a look at this particular one and see how it works out. I'll be honest with you, even though the type 1 requires 2 regions, in some ways it's a bit simpler to solve. There's more work, but the work itself is less difficult. Let's take a look at why that happens. If we decide to work it as a type 1, then we're looking for a function above and a function below that doesn't vary. In that case, we're going to draw long vertical rectangles to indicate which function is on top and which is on bottom. We can see that there is a change right there when x equals 2. This will give us two different regions. In both regions, we have the function y equals 0 on top. In the region on the left of x equal 2, we have the left arm of the parabola on the bottom, or x squared minus 4x. On the right side, between 2 and 4, we have that the line y equal 2x minus 8 is on the bottom. This would require us to split it into two values. Notice that I went ahead and set the equations equal to each other and solved systems in order to find out what the values of the ordered pairs at the points of intersection are. I found that the point here was given by 0, 0, and the point here is given by 4, 0. I also found that the point down here is given by 2, negative 4. Once I had those values, then I knew I could work it as either type 1 or type 2. Let's follow through with the type 1 work. If we do it as a type 1, then we have two regions, which you can see here, the purple, which is labeled A, and the black, which is labeled B. I went ahead and did side A first and then side B separately, though of course you could write them at the same time. Side A is the integral from 0 to 2 of with respect to x on the outside, and the inner integral is from x squared minus 4x to 0 of 1 dy. When we integrate 1 with respect to y, we get y. Substituting the limits of integration, because 0 is the upper, we get negative x squared plus 4x. Now we can integrate this with respect to x, and when we simplify, we get 16/3 square units. That's the amount of area on the purple side on the side A. Then we set it up again, but for side B, where we are going from x equal 2 to x equal 4 on the outside, and the y goes from the line y equal 2x minus 8 to the line y equals 0 above. This time, when we integrate with respect to y, we again get y, and we evaluate between the limits of integration. Because the 0 is the upper, this gives us negative 2x plus 8. When we integrate that, we get negative x squared plus 8x, evaluated from 2 to 4, which gives us 4 after simplification. That means that the area in region B is 4, which upon inspection, we probably could have figured out using a right triangle. Then we add side A and side B together, which gives us 28/3 square units for the area between the parabola, the line, and the x-axis. If we wanted to work it as a type 2 problem, we would instead be drawing horizontal boxes and looking for what is going to divide it this direction. When you draw your horizontal strips, notice that you're always hitting the left arm of the parabola on the left side and the line on the right side. This becomes one region as a type 2, which may make it easier to solve depending on the equations you get when you solve them for x in terms of y. In this case, we're given the parabola x squared minus 4x. Unfortunately, we can't solve it directly for x because x shows up in two terms. In order to do that, you need to complete the squares you'll see at the bottom in the lower left corner. We add 4 and subtract 4, then we factor the first three terms as the binomial x minus 2 quantity squared, then we have a minus 4. This, of course, is putting it in a different format. Once we do that, we can solve for x minus 2 by moving the 4 to the right by addition and taking plus or minus the square root. We know by inspection of the region that it's the left arm, so we're interested in negative the square root of y plus 4. But this doesn't give us x, it gives us x minus 2, so we add 2 to both sides to get the rewritten function of y, 2 minus the square root of y plus 4. That is going to be more difficult to work with in integration, but of course it is possible and we'll do it. We'll take the line y equal 2x minus 8 and solve for x to get y divided by 2 plus 4. Now that we have these, what will the outer integral go with respect to? The outer integral in this case is going to go from y equal -4 to y equals 0. The inside will be from y equal, let's see, on the left, we will have the parabola 2 minus the root of y plus 4. And on the right, we have the line. Let's go ahead and look at it as a type 2. As a type 2, you can see on the outside, we have the integral from -4 to 0 with respect to y. And on the inside, we have the integral of 1 dx from the parabola to the line. Of course, the integral of 1 dx is just x. And when we substitute the limits of integration, we get y divided by 2 plus 2 plus the root of y plus 4. The first two can be integrated directly, giving us y squared over 4 between -4 and 0, and 2y between -4 and 0. When you work these two out, you get -4 plus 8, or 4. The third one, however, needs to be done by u substitution, where u is the y plus 4 under the square root. Du will be dy, and then we change the limits of integration such that when y is -4, -4 plus 4 gives me u equals 0. When y equals 0, 0 plus 4 gives me u equal 4. This gives me the integral of u to the 1/2 du between 0 and 4. When I integrate that, I get 2/3 u to the 3/2 power between 0 and 4, which gives me 16/3. When I add that to the 4, I get 28/3 square units, which is the same value I got working it as a type 1. We're now ready to take a look at the last application of double integrals over generalized regions, and this is finding the average value. In this case, it makes sense that we solve these essentially the same way we did in section 5.1. First, we find the net volume by calculating the double integral of the function of two variables with respect to the differential dA. Then we take this volume and we divide by the area from the domain that was restricted. When we take the volume and divide by area, we should end up with the average height or average z value for every rectangular prism that would give us a solid with the same net volume as between the surface f of x and y and the xy plane. In order to complete this, then, we need to complete different integrals. First, we need to find the net volume by calculating the double integral of the function over the restricted domain D. Then we need to calculate the area, which essentially becomes another double integral where the integrand is instead 1, and this will allow us to then compute the average height or z value. Let's take a look at example 9. In example 9, we want to find the average value of the function cosine of x, but restricted to the region graphed in the picture. The region graphed in the picture goes between the vertical lines x equals 0 and x equal pi over 2. We always have the curve y equal 1 plus sine x in the numerator, and we always have the curve y equal sine x in the denominator. This makes this an ideal type 1 region. In order to compute the average value, we need to find two different double integrals, the net volume over this restricted domain and the area between these two curves, which can be solved using calculus 1 techniques, but obviously can also be solved using a double integral with an integrand of 1. Remember that our function in this case is cosine of x. This is actually going to give us a cylinder based on cosine of x, like taking the cosine of x curve and pulling it along a line. Go ahead and pause the video in order to find the area of this restricted domain and then to find the net volume between the surface cosine of x and the xy plane over this restricted domain. Then take the net volume and divide by the area to get the average z value. When you're completed, go ahead and turn the video back on and we'll work it together. In this problem, we can write our restricted domain as the set of all xy ordered pairs such that x is between 0 and pi over 2, and y is greater than or equal to sine of x, the curve on the bottom, less than or equal to 1 plus sine x, the curve on the top. Our function of two independent variables, x and y, is cosine of x. This gives us a surface in three-dimensional shape, which is actually the cylinder cosine of x being pulled. We don't actually need the function of two independent variables cosine of x to find the area. To find area, we set the integrand to be 1. In this case, we're working it as a type 1 problem. And when we find the area, we're going to integrate on the outside from 0 to pi over 2 with respect to x, and on the inside from sine of x to 1 plus sine of x of 1 dy. The integral of 1 dy just gives us y evaluated between the limits of integration. Note that the sine x cancels, which gives us a new integrand for the outside function of simply 1 with respect to x. This gives us x, which tells us that the region in the domain that we've restricted the function to is pi over 2 square units. When we're talking about pi over 2 square units, we're talking about the number of square units in the blue shaded region coming from the restricted domain. To find the average value of the function over that restricted domain, I next need to find the net volume over that restricted domain. Since it's a type 1, I set it up with the same limits of integration, but this time to find net volume, I use the function of two independent variables, cosine of x, as the integrand. Since cosine of x does not depend on y, it's considered a constant. So that simply gives me y times the cosine of x. Then I evaluate that between sine x and 1 plus sine x, and again, the sine x's cancel. That gives me 1 times cosine x, or simply cosine x as the new integrand for the outside integral. This will give me the integral from 0 to pi over 2 of cosine of x dx. The integral of cosine is sine of x, and evaluated between 0 and pi over 2, I get 1 cubic unit. In other words, between the cylinder, which is cosine of x, and the xy plane, I have a net volume of 1 cubic unit, 1 in each of the dimensions. To find the average value, I next take the net volume and divide by the area of that restricted domain, D. This gives me 1 over the area function of D multiplied by the double integral over D of cosine of x with respect to the area differential. I can use the values I found, 1 cubic unit divided by pi over 2 square units, to get that the average z value that would give me the exact same volume is 2 divided by pi. Let's now take a look at what it looks like on CalcPlot 3D. In CalcPlot 3D, I first went ahead and graphed cosine of x, and I spread it out a little bit so that you can actually see here the cylinder, which is corresponding to the cosine of x function. And if I can get it turned exactly right, we'll be able to see that curve a little bit better. Now, if I turn it back the other way, what I'm looking at here when I turn it around is I'm looking at just the portion of it restricted to what I wanted to see before. So if I'm looking at it now, what I need to have it restricted to the region between sine of x and 1 plus sine of x, x between 0 and pi over 2. I open up a region and I set those as my top and my bottom, and x to be restricted between 0 and pi over 2. Let's take the cylinder off so that we can see our region a little bit more clearly. Now you can see it. It almost to me looks like part of a spiral staircase kind of coming down. And what we've got here is the prisms that are creating this shape on the restricted domain. Again, you can see in the 2D trace plane the restricted domain over which we are evaluating the net volume. In this case, it got a net volume of about 0.697. The exact volume, of course, we know is supposed to be 1. In order to get a better approximation, we would need to take more prisms in each direction. You could perhaps do 37 in one direction and 37 in the other, and notice that we're now much closer to the true value of the volume, which is 1 exact cubic unit. We now have 0.9 cubic units. If you want to see the shape without all of the prisms, click on the box Show Riemann Prisms to turn it off, and then you'll be able to see the shape coming down. It almost looks a little bit like a ramp as well, if you want to think of it that way. What does this mean? This shape has exactly the volume of 1 cubic unit. If I were to draw a solid such that the base of it is the same domain, the height of every z value should be 2 divided by pi to also give me 1 exact cubic unit of volume. Let's see if we can do that now. In order to find the solid that has the same volume but a uniform height, what we want to do is open up another region. We're still going to have y plus sine x as the two-dimensional top based on the 2D trace plane that we see up here. We want the bottom of the 2D trace plane to be the function sine of x and x to vary from 0 to pi over 2. This time, however, we want the top surface of our solid to be the constant value 2 divided by pi, and the bottom to be the xy plane where z is 0. When we do this and we take more Riemann prisms, 37 in each direction, we get an approximation for the volume of about 0.9. Let's see, I believe it will be in the upper green ribbon. This is about the same as what I got with the other with the same number of prisms. In order to get it to be closer to 1, I would have to take more prisms. The more prisms I have, the closer it will be to the true value, which is 1 cubic unit. Let's now turn our attention to the next example, which is improper double integrals. Improper double integrals are somewhat similar to what we saw in Calculus 2. In Calculus 2, there were 2 types of improper integrals. Just as in Calculus 2, not all improper double integrals will be able to be evaluated. Some of them simply will not be. One of the types was when one or both of the limits of integration was infinity, and this, of course, is a Calculus 2 problem. How is that going to apply in a Calculus 3 problem or multivariable calculus? Since we have double integrals and we know that we might be expanding with respect to x or y, what this means is that one of those or both is allowed to extend forever in a particular direction. For example, we may say that x can go to infinity, or that y can go to infinity, or both x and y can go to infinity. We could also, of course, go to negative infinity for x or negative infinity for y. In that case, our limits of integration in the double iterated integral, one of them will become improper, or perhaps both, at infinity or negative infinity. The other type of improper integral in Calculus 2 came from a vertical asymptote somewhere between the lower limit of integration and the upper limit of integration's value. Looking at this integral here, the integral from 1 to 5 of x divided by the quantity x squared minus 2x minus 8 with respect to x, we can factor the denominator to get x minus 4 and x plus 2 as factors. This has two possible solutions that would cause the denominator to be 0, resulting in a vertical asymptote in the graph of this function. One is at x equal 4, the other is at x equal negative 2. However, only one of those values is between the limits of integration 1 and 5, and that's 4. The way that we handled this in Calculus 2 was we had to split the integral, taking the limit as c approached 4 from the left of the integral from 1 to 4, plus the limit as d approached 4 from the right of the integral from d to 5. Let's see how we're going to deal with these in the three-dimensional space when we have functions of two independent variables. Basically, we have an improper integral in three-dimensional space if either the region D over which we're integrating is unbounded, meaning one or both limits of integration are going to plus or minus infinity, or the function for the surface is itself unbounded, meaning that the z value goes to infinity or negative infinity, very similar to what we saw in the case in Calculus 2. Again, we're going to restrict our focus to integrals over unbounded regions D, or where the function value, the z value, goes to infinity somewhere in the rectangular or simple region given by D. Let's look at Fubini's theorem for improper integrals. If D is a bounded rectangle or a simple region, meaning closed and bounded, in the plane defined by, well, not closed necessarily or bounded, but simple, x between a and b and y between g of x and h of x, a type 1, but it could also be defined as the set of all ordered pairs x, y, where y is between c and d, and the x is between j a function of y and k a function of y, type 2, and f is not negative on this restricted domain D, and it has only a finite number of discontinuities, possibly asymptotes, in the interior of D, then we can say that the double integral of the function over that restricted domain D is given by the iterated integrals in either order, depending on whether you define it as type 1 or type 2. In other words, we have some conditions here that we did not have in Calculus 2, namely that the function has to be non-negative. It can be 0, but it can't go below the xy plane. It has to stick on the xy plane or above. And if it has discontinuities, including asymptotes, then we must only have a finite number of them. If we have a finite number of them and they're in the interior of this region, then we can simply integrate as we normally have. Note that the function is going to be allowing us to find the value of it without having to break it up at the points of discontinuity. In calculus 2, if 4 was a vertical asymptote point and it was between the limits of integration, such as 1 and 5, we had to split the integral into two parts at 4. In a function of two independent variables in three-dimensional space, we do not have to do that. We can simply evaluate as we normally have. This is very different from calculus 2. In calculus 2, we had to split it, as you see here at the bottom. But in multivariable calculus, we can simply plow right over it all. And as long as there's only a finite number of discontinuities, it will still give us the correct value. What about if we have an unbounded region, meaning that x or y is allowed to go to infinity? The previous case was looking at vertical asymptotes of the surface, where the z value goes to infinity. In this situation, the z value is probably restricted and not going to infinity, but the domain region over which we are evaluating it is extending to infinity or negative infinity in one or both directions. In this case, we do have to split it, and we take the limit as BD approaches infinity to infinity. In this case, notice that x is between a and infinity and y is between c and infinity. In this case, we'll take the limit as BD approaches infinity and infinity of the iterated integral. Again, whether it's type 1 or type 2, depending on which way you want to set it up. Probably the best way to see these is simply to do an example. Let's go ahead and take a look at example 10 now. When we look at example 10, we have our function of two independent variables of y divided by the square root of the quantity 1 minus x squared minus y squared. When we think about this region, we know that we cannot allow the denominator to be 0, because if we do, we must have a vertical asymptote in the surface. If we're looking at that, then we're going to be restricting our domain to where it was given, which is x greater than equal to 0, y greater than equal to 0, and x squared plus y squared less than equal to 1. If both x and y are greater than equal to 0, then we're now restricted to quadrant 1. If we're looking at quadrant 1, and we have it restricted further that x squared plus y squared is less than equal to 1, what we have is a restricted domain of the quarter circle in quadrant 1. Now, the problem with that is if I were to factor this denominator and I were to take out the negative, I could rewrite this as the double integral over that region D in quadrant 1 of y divided by the root of 1 minus quantity x squared plus y squared. In this case, if I'm looking at it like this, if x squared plus y squared equals 1, I'm going to have a problem. I'm going to have a 0 in the denominator. When does x squared plus y squared equal 1? Well, basically, everywhere along the edge or boundary of this region on that quarter circle that we see in quadrant 1. However, that is a boundary point, and the rule is that we have to have a finite number of discontinuities on the interior of the region D. Are there places where the interior might come out that way as well? When we're looking at these, none of our points where x squared plus y squared equals 1 is actually in the interior of the quarter circle. Even though it is improper on the boundary, we are allowed to simply go ahead and integrate like normal, and we will get the true value. In other words, we're going to simply go ahead and integrate as if it were not improper on the boundaries at all. When we look at this, we need to come up with some kind of relationship for y. We have that y is greater than or equal to 0, but we need to represent this quarter circle in terms of y as a function of x to make it a type 1. Using the equation x squared plus y squared equals 1, I can write y squared equals 1 minus x squared. And since it's part of the upper part of the circle, I get y equals 1 minus the square root of the quantity 1 minus x squared. This will give me my limits of integration. Let's go ahead and write down the limits of integration for that particular domain. Notice that in this case, my domain can be written as the set of all ordered pairs xy, such that x is greater than or equal to 0 and less than or equal to 1, and y is greater than or equal to 0 and less than or equal to the square root of 1 minus x squared. This is creating this region here as my region D. Then we can set up our improper integral. Our double integral of that particular function can be written as an iterated integral, such that the outside integral goes from 0 to 1 with respect to x, and the inside integral goes from 0 to 1 minus x squared with respect to y. Then we have y over the square root of 1 minus x squared minus y squared with respect to y first on the inside, and then with respect to x on the outside. Notice that we cannot separate this into two factors that depend only on a function of x and only on a function of y. In order to complete this, you're going to have to use some substitution. Go ahead and pause the video here to work out this integral, then turn it back on so we can work it together. You're going to find that this problem has a great deal of calculus 1, 2, and 3 in it. It's a rather complicated problem. Again, we're dealing with a bounded region consisting of the quarter circle in quadrant 1 of radius 1, but an unbounded function along the boundary of that quarter circle where x squared plus y squared equals 1. So the denominator of our function goes to 0, meaning the z value goes to infinity. Because the points where it is equal to 0 are not on the interior of the domain D, we are able to go ahead and integrate like normal. In this case, I went ahead and wrote the expression for the region D over which we're integrating as the set of all ordered pairs such that x is between 0 and 1 and y is between 0 and the square root of 1 minus x squared. Note that the square root of 1 minus x squared is coming from the fact that on the quarter circle, x squared plus y squared is 1, so y squared is 1 minus x squared, and we get the square root of 1 minus x squared, giving us part of the top half of that circle. When we put these into the double integral and write it as an iterated integral, we get the integral on the outside from 0 to 1 with respect to x, and the integral on the inside from 0 to the square root of 1 minus x squared of the function y over the root of quantity 1 minus x squared minus y squared with respect to y. In order to do this, we need to use substitution. This, of course, is calculus 1. Our u is going to be the part that is underneath the radical or the radicand. U becomes 1 minus x squared minus y squared, but we are integrating with respect to y. The differential is dy, so we take the derivative of u with respect to y. The 1 and minus x squared are considered to be constants, so they zero out. The derivative of u with respect to y gives us negative 2y, and we abuse the notation and swing the dy around. We have a y dy inside the integrand, which is the same as du divided by negative 2. To change the limits of integration, when y equals 0, we get the expression 1 minus x squared. When y is the square root of 1 minus x squared, and we substitute it into this definition for u, we actually end up with 0. This is going to give us the inside integral from 1 minus x squared to 0 of u to the negative 1/2 times du over a negative 2. The next thing that we can do, of course, is go ahead and integrate, which is going to give us a negative value coming in, resulting in negative 1 times u to the 1/2 power evaluated between 1 minus x squared and 0. Because we have the negative, we can reverse the limits of integration so that we have a positive u to the 1/2 integrated between 0 and 1 minus x squared. This is simply going to give us the integrand for the outside integral of root of 1 minus x squared. However, to integrate this, we need trig substitution, which is calculus 2. We allow u squared to be x squared so that u is x, and a squared to be 1, so a is 1. This has the form of a constant minus a variable thing squared, so we use sine. Our substitution equation is u equals a sine theta, or x equals 1 sine theta. Putting this back in the expression under the radical, 1 minus x squared can be written as 1 minus sine squared, which becomes cosine squared. In this way, we go from 2 terms to 1 term. Then we need to find the derivative of x with respect to theta, which, since x is sine theta, gives us cosine theta d theta. Substituting each piece into the original integrand, we get the square root of cosine squared, which gives us cosine theta, times another cosine theta, d theta. This will give us cosine squared of theta d theta. Notice I did not change my limits of integration since I intend to go ahead and stick with x from 0 to 1. In that case, I have to write the x equals 0 and x equal 1. I integrate further by looking at this as a trig integral, which again is calculus 2. I rewrite cosine squared as 1/2 times the quantity 1 plus the cosine of 2 theta. I split that into 2 integrals, getting 1/2 the integral of 1 d theta, which gives me 1/2 theta, evaluated between x is 0 and x is 1, which I cannot do until I can get back to x. The other integral is 1/2 the cosine of 2 theta, for which I need calculus 1 again, use substitution. This time, since I've already used u for something else in our trig substitution, I'm going to use omega, or w. This gives me omega is 2 theta, or d omega is 2 d theta, so d theta is d omega over 2. Substituting this in gives me 1/4 the cosine of omega d omega. When I integrate, I get 1/4 sine of omega, but again, my limits of integration don't match my variable, so I cannot substitute them. Then I return omega to its value of 2 theta. Now both terms are written in terms of theta, so it's time to go back to the trig substitution equation, x equals sine of theta. If x is sine theta, then x divided by 1 is also sine theta, and the arc sine of x is equal to theta. That will allow me to replace theta in the first term. However, I have sine of 2 theta, but everything from the trig substitution is in terms of theta. That means that I have to rewrite the sine of 2 theta using a double angle. I rewrite it as 2 sine theta cosine theta, which will give me 1/2 sine theta cosine theta. But I know what sine theta is. It's x. I need to find cosine of theta, so I draw a triangle where the ratio of sides tells me that the sine of the angle is x divided by 1. That makes the adjacent side the square root of 1 minus x squared, which is what I started with in the trig substitution, so I know I've done it correctly. Finally, I replace each piece with what it had. In the first, I have 1/2 arc sine of x between 0 and 1. For the second, I have 1/2 x times the square root of 1 minus x squared between 0 and 1. The arc sine of 1 is pi over 2, and the arc sine of 0 is 0. That gives me 1/2 of pi over 2, or pi over 4. Substituting in the limits of integration on the second term, they both lead to 0, which gives me a final result of pi over 4. This represents, of course, the net volume between the surface and the xy plane, even though on the boundary of this surface it goes to infinity. Let's take a look at what the surface looks like. You can see an image of the surface here. Let's take a look in CalcPlot 3D. In CalcPlot 3D, this is our image, which is restricted to just the domain in question. Notice that the z values are not quite finished. They're climbing ever higher and higher. On the boundary, z is unbounded. On that quarter circle, it goes to infinity. We're trying to find the volume of the solid underneath the surface and above the xy plane. If you want, you can put the surface on again, which will show you a little bit more what it might look like if you have the whole thing there. CalcPlot 3D does have a little bit of trouble in drawing this particular one, so don't be surprised to see some weird things popping out the side like right there. They don't actually belong there. That's not actually part of it. It's having trouble because of the unbounded nature of the z along that quarter circle. Let's now take a look at our last example in this section. We have example 11, which is to evaluate the double integral over a region R with the function being 1 divided by the quantity 1 plus x squared times the quantity 1 plus y squared with respect to the area differential. This time our region is given by x greater than equal to 0, y greater than equal to 0. There's no value in the function that will cause the denominator to be 0. So our function, this rational expression, is in fact bounded over any region. We can never make the denominator 0 because squaring something makes it a minimum of 0 and adding 1 makes it a minimum of 1. However, the region over which we are integrating our d is in fact unbounded. When we say x greater than equal to 0 and y greater than equal to 0, what we're talking about is the entirety of quadrant 1. We're talking about all this space forever and ever and ever and ever, extending both to the right and up forever and ever. While the function is bounded, the z values are bounded, the domain over which we're integrating is not bounded. Let's now talk about how we might set this up. The other thing to note here, of course, is that the region over which we're integrating is, in fact, in a sense, rectangular, because it is quadrant 1, which, well, is rectangular. So because of that, we can actually solve this as if it were a problem out of section 5.1. We need to integrate where x goes between 0 and infinity, and y goes between 0 and infinity as well. When we do this, We can also make use of the fact that the denominator can be separated into factors that depend only on x and only on y. We should be able to separate these and solve them as single integrals as well. We'll solve this first as a double integral, then we'll take a look at it as a single integral. Go ahead and pause the video to write down the integrals, then turn it back on and we'll get started. Let's take a look at what's involved in solving this improper integral without noting and taking advantage of property 6, which splits it into two integrals of a single variable multiplied together. If we did it as a double integral instead, we're going to integrate from y equals 0 to infinity on the inside and from 0 to infinity with respect to x on the outside. In order to integrate what's on the inside, remember that the 1 over 1 plus x squared part is just considered a constant. We only pay attention to 1 over 1 plus y squared, which requires trig substitution. We set y to be tangent of theta so that 1 plus y squared can be replaced with 1 plus tangent squared or secant squared. dy then becomes secant squared of theta d theta, and theta would of course be the arctangent of y. When we make our substitution, this gives us the integral of 1 over 1 plus x squared times secant squared in the denominator times secant squared theta d theta in the numerator. The secant squareds of theta, of course, will simply cancel, and this leads us then to be able to write that we have the integral evaluated between 0 and c. This is going to give us the integral of 1 over 1 plus x squared d theta, which gives us 1 over 1 plus x squared of theta, evaluated between 0 and c, where we're taking the limit as c goes to infinity. The 1 over 1 plus x squared does not depend on c and could in fact be pulled out. This gives us the arctangent of y. The angle whose tangent approaches infinity is pi over 2, and the angle whose tangent approaches 0 is 0. This then will give us, of course, pi over 2. This gives us the outside integral of pi over 2 multiplied by the integral from 0 to infinity of 1 over 1 plus x squared dx, which is essentially the identical integral that we just solved using trig substitution. You can use the same trig substitution and get pi over 2 times the limit as c goes to infinity of the arctangent of x evaluated between 0 and c, where we're taking the limit again as c goes to infinity. The angle whose tangent gives us infinity is pi over 2, and the angle whose tangent is 0 is 0. This gives us pi over 2 times pi over 2, or pi squared over 4. This is a rather difficult problem to solve without taking advantage of property 6. Let's take a look at the same problem, but using property 6 to turn this double integral into the product of two single integrals of a function. In this case, I can split the integrand into the product of 1 over 1 plus x squared times 1 over 1 plus y squared. This gives me two functions, one a function of x only, one a function of y only, that are multiplied together to give me the integrand. Since I know that the function is continuous over it, since it's never undefined, then on my region, I can split it into two single improper integrals. This gives me the integral of 1 over 1 plus x squared, which we've already done, and which you may just recognize as being arctangent of the argument. In this case, we again get pi over 2 for each one and multiply them together to get pi squared over 4. Let's take a look at what this looks like out on CalcPlot 3D. In CalcPlot 3D, we have an unbounded region in our 2D trace plane. It's only showing from 0 to 10 in both directions, but in fact, it extends forever up and to the right in quadrant 1. When we look at our surface, you can see that the surface is almost like a blanket covering everything that's been pulled up to a certain value along the z-axis. If we're looking at it restricted to just the region over quadrant 1, then we'll get a smaller area. Let's take the entire surface off and just look at the surface there in quadrant 1. Now you can see that you've got this area here, which is sort of like the edge of the blanket drawn up towards z equal 1, and the rest of it just slightly above the plane in all directions. Since z is never equal to 0, we know that the surface never actually touches the xy plane, though it gets arbitrarily close. When you're approximating on this one, you can get an approximation of about 2.164, which in our case is, well, let's see, squared divided by 4. The true value is around 2.467, so it's not too terribly off. However, I am using quite a few prisms already, 40 in the x and the y direction, but this unbounded region is going to require a great many more prisms to get a more accurate approximation of the net volume of this solid created by the surface over the xy plane. I know this has been a rather long section, and it's taken a while to get through all the material because it is a bit more complicated than integrating over a rectangle in the xy plane. In our next section, we'll take a look at solving problems such as the last one, instead using polar coordinates, which will make some of these problems far easier to compute than using them in their x squared plus y squared form. I hope you'll join me for that video.